Thanks a lot. I'm really grateful for the invitation to talk here. This has been a very interesting conference, and many thanks for that. This was my initial idea to talk about measurement decoherence and collapse, but then I thought about talking about a few other things. So I combined a discussion on two not so easy problems. First of all, there is the measurement problem, and then the information paradox in black holes. Now, clearly, I am not going to say things which will solve in any way these very serious problems, but I would like to suggest a new approach which very surprisingly will be connected to time-symmetric formalism of quantum mechanics. And I think the idea here is one which I studied from Yakira Aronov and later on by Lev. Quantum, and not only quantum, but physics paradoxes drive us to further explore nature, and we always learn something new from a quantum paradox. So this is what I'm trying to do here. And just a little preview. Yesterday Avshalom took me to see this clock, and I realized it is strictly connected to my lecture. So you probably know it because most of you are from here. I just have two comments. The first one is I hope to be a little more accurate than exact every 5 minutes. And what this clock telling me is time is very precious, and this is among other reasons why I chose to give a risky talk. I will be probably criticized by the first part by quantum physicists and later on by general relativistic, but I think the ideas are worth talking about. And now the outline will be very, very easy, very simple. I want to know in what sense can non-unitary process be reversed. And in fact, we have an answer. As Lev could say, the many worlds interpretation immediately solves this problem. There is no non-unitary processes. Everything is reversible. But I am interested in another kind of time reversal. And I want to show that even in a single branch of the many worlds interpretation or in any other formulation, time can be reversed when applying a certain boundary conditions and certain assumptions about what can be reversed and what can't be reversed. The natural thing to do is extend this approach to black holes, I think, which poses a much serious problem. And I might talk about free will. I'm not sure yet, but I have free will, so I'll just decide later. The motivation is 3 arrows of time. The 3 is kind of fate because I'm not really sure there are 3 different arrows, and probably there are more, but for this talk I'll mention only 3. The first one is the thermodynamic, and you know, if I start with a box when all the gas particles are located in one part, and then I open the intermediate part, the gas will spread, and we know that there is a final boundary condition on this gas which will turn it back to the final, to the initial state. Another, I'm getting used to this, okay, so this let us define the arrow of time in terms of stability under random perturbations, because we know that the forward arrow of time is more tolerant to random perturbations than the backwards. This is probably known, and also we have the quantum error of time. If we have gas of particles in superposition and we perform a strong measurement, a collapse on one of them, we will have some problem of reversing this process, not in the many worlds interpretation, but in our, not God's picture, but our more moderate picture of the world. So this is another time error, and I think we can reverse it as well when we consider macroscopic objects. The third and most hard problem is the extreme cosmological time error, which means that if these particles enter a black hole, it will be very hard to reverse the process and let out all the information. Now I'll say a few things which all of you know, but this way I would get less offensive remarks, maybe. So we know that Hermitian Hamiltonians give rise to unitary time evolution. This evolution can be easily reversed if we just take the Hermitian conjugate, and we can just look at the process on equal footing, forward to backward, backward to forward, no problem, as long as we don't insert the collapse. When we have collapse in our theory, we have a problem, of course, with unitary, and then it is believed that time cannot be easily reversed. And this is a real problem, which Gottfried mentioned here. This takes a beautiful thing in the quantum theory and ruined it. So I try to reverse this. And again, we have an alternative which is good and it gives a full solution, but I try to find an alternative. And each alternative has benefits and disadvantages, but you'll see that. And being Jewish, before considering the alternative, I asked some other very related questions. And I want to ask some questions about the measurement problem. So first of all, we are not sure how to determine the limit between classical and quantum physics. We are not sure either how and when exactly the wave function collapses, and why a certain outcome is reached rather than another one, although we do know that the Born rule gives us the right result. So I think the important question here is not whether the cat is dead or alive. The question is whether the cat is dead or alive. Do we believe that the cat describing the dead cat is here in somewhere after we perform the measurement, or it is gone forever? And using a time decoherence process I'll show you, I think that the cat of the cat is alive but suppressed by the future boundary condition. The scheme is again and only natural. We start with a final and of course initial state. Then we have a process of backwards evolution, and using the two-time decoherence we try to retrieve information. We do it both on Euclidean space and then try to do it on the Schwarzschild matrix. So another review, all of you know, so I'll be quick. The beginning of this kind of time-symmetric formulation was in 1964 when Aharonov, Bergman, and Leibowitz suggested their time-symmetric formula for quantum probabilities. And you can see in this equation that both the backwards evolving phi state and the for the evolving psi state are symmetrically determining the probability. This was later broadened to a more, I think, maybe, I don't want to say it is now broader, but the ontology is richer, and we do think about these two-time density matrices which determine our state at the present. All of this was very hard to verify this two-state vector formalism, and in 1988, Aronov, Albert, and Weidman made a very important contribution when suggesting weak measurement, and you already seen that these kind of measurements are very fruitful. There are only 3 examples here why TSVF and weak measurements are important on the conceptually important. Lev showed you the past of a quantum particle. Sandro is not here, but is one of the authors of the Cheshire Cat, and Avshalom talked earlier about our weak Bell experiment. And each of these experiments, I think, tells us something about the quantum reality we didn't see before we talked about post-selection. Lev's experiment gives a surprising result, which we perhaps could not anticipate. Also, the Cheshire Cat tells us something important about entanglement and about physical values. In our experiment also, besides the conceptual gain, we also have experimental gain. Weak measurements are not important only as a conceptual tools, but they enable us to perform precision measurements. They were used to demonstrate for the first time the spin-Hall effect for photons. They are helpful in quantum tomography. We are able to see using them the average Bromian trajectory, which is not a well-defined, not so well-defined beable in the experiment, and also the important tool of super oscillations, which is now growing, I think. And we have this combination of experiment and concept, which among many other experiments we try to achieve these days together with a group in Torino. The question is, like Raphael asked before that, is it possible to take this very, very fruitful formalism and use it to analyze problems taken from a cosmological scale? And I think the answer is yes. I start with the two-time decoherence process. There is some math, but I'll go over it quick again. We start with a combined state of a particle, alpha 1 plus beta 2 on a two-level system. We have a quantum pointer prepared at ready state, and we have the environment at epsilon naught. Now we are making a von Neumann measurement at time t1 and couple this particle to the measuring device. So what we do, we take the microscopic description of the particle 1 and 2, and then we have the combined description together with the pointer, when the pointer states 1 and 2 are almost orthogonal. After a short time, as we all know, this system decoheres, and instead of one environmental state, we get 2 states, which are many particle states. The importance of these states is they encode the very, very fragile microscopic information. And these states, epsilon 1 and epsilon 2, will be the one which will enable us to reverse the process. The crucial part, of course, is using some post-selection of the system. And this post-selection is somewhat unique because it contains only a single term of the preferred basis chosen by the environment. But in fact, it can be seen that it chooses the pointer basis and chooses the outcome we got. This is not the most general post-selection. We can insert some some more terms with small amplitudes, but essentially this is the post-selection we want. And now, within the TSVF, our system will be described by this two-time density matrix. And you can see by the orthogonality that the reduced density matrix of the pointer plus particle state is exactly what we got in our experiment. It is 1 together with 1 of the pointer, and this is in fact this is an approach to understand what we see in nature. And also, every weak interaction we could have done during this time would have been determined only by this term in the future. So it really describes the macroscopic reality we see now. This is at least my opinion. And now we generalized this work. I skipped the slide probably, but this work was accepted this morning for publication in Quantum Studies, the new and very recommended journal Lev talked about. And what we did there, we talked also about the more tough case of multiple measurements one by one, about continuous pointers which are harder to encode, about mixed state, and finally about the full description of nature when the macroscopic world is not different than the microscopic world. It can also decay. It can also collapse. And I'm now getting to the main idea of this part of the talk. What we want to restore is not the single particle state. We want to restore our experience, our macroscopic experience. So we don't pay much attention to collapses in the microscopic world as long as they are encoded in the macroscopic state, which will backward evolve to enhance one of the possibilities. And in order to generalize this approach and supposedly advance in understanding the measurement problem, we need to remember only two things. First, that collapse never leads to an orthogonal state. We know this well. And the other is there cannot be too many collapses. I'll return to it later, but I think it is obvious that even theoretically, not practically, we will not be able to encode n macroscopic n, 10 to the power of 23 degrees of freedom, ever. And these are my assumptions. So we have again this state at the intermediate time after decoherence. And now we use our assumption that out of macroscopic n degrees of freedom, only n, which is much lower than prime n, collapse. So the states, again, this is a little simplified description, but I don't think there is something fundamentally oversimplified here. And what we get is a bunch of collapsed states, but most of the states survive the collapse. This is an important point. The macroscopic world we know would not collapse until the second part of the talk. And we know that things never collapse to an orthogonal state, so the inner product must be different from zero. The final state is chosen in the same way, and now we define what I think can be used in order to define the border between micro and macro. We look now on the probability to get from the future the right state, which we already got, and the probability to get the wrong state. Because we are talking about macroscopic systems, this ratio is very, very large. The probability to get a macroscopic number of degrees of freedom collapsed wrongly is very, very low. So this ratio depends on n, the two n's, and when we think about the connection between them, I think we can understand better what makes things classical and what makes things quantum. Classical things can easily be obtained, while the quantum generally cannot. We also show the derivation of the Born rule, but there are many derivations, and I don't really believe in deriving Born rule, so this appears in our work. The significance, in my opinion, is that the many words interpretation was initially invoked in order to eliminate the collapse. The problem is, although this is a very productive interpretation, it involves infinitely many words, which we cannot measure with our technology, not super technology. And now we have a formalism which lets us time reverse also one single branch. And the possible criticism would be that the final state is very spatial and very artificial, and I think there could be several answers. The first one is the initial state is also very unique, and I don't think there is something wrong with that. In my approach, this is nature. Nature is unique, and it poses unique pre- and post-selected states on the universe. Moreover, I think that this artificial, I don't think it is artificial, but it is spatial boundary condition, it is not worth as spontaneous collapse or invoking infinitely many words. And the last thing, which is the matching, which is the important one, under our assumptions, there is a unique family of possible final states. That is, we don't have, the state is not arbitrary. It is determined by the way we currently see nature. The second objection could be that for large, very large n, this process will fail. But as I said earlier, I can show both on microscopic and cosmological state that n cannot grow to infinity. N will always be bounded. So I don't think this is a problem either. Okay, now moving to general relativity, I'll try to use the same formalism in order to talk about the black hole information paradox. You can already see here a nice experiment. I don't know which group did it, but here is Schrödinger cat's enters and exits a wormhole. Okay, not everyone here is familiar and sick, and I'm also not an expert. But this is a very, very condensed review of the last 40 years, I think. The beginning was probably Carter's work when he showed that the only solution of the Maxwell-Einstein equations is the Neumann-Kerr black hole, which possesses only mass, angular momentum, and charge. This is known as the No-Hair theorem. But several years later, Bekenstein thought, and Hawking showed, that black holes radiate, and that means that this information we had now is probably disappeared. Hawking immediately said that general relativity is true, quantum mechanics is probably not unitary, and this was the immediate conclusion. Later on, people like Susskind described better the process and talked about, still talking about black hole complementarity. That is, two distinct observers see different kinds of processes. One which is in falling, it reaches the singularity infinite time, and it knows that the information reached the singularity. The other one outside would not see it until infinity. As I said previously, these kind of problems are very, very thought-provoking, and one of the important thoughts, I think, is the holographic principle suggested by Tufte. It was later described within the ADS-CFT correspondence, and I'm not sure that string theory or M theory would serve the solution, but it clearly sheds light on what can we do with black holes, how to understand the information on their boundary in unitary fashion with CFT. Last year, another paradox emerged, and this is the AMPS paradox. And I'll go now to it. I'll skipping now, but currently their proposal, their only options are either black hole is really non-unitary, as Hawking thought on the beginning, or there is some kind of very, very energetic shell outside the black hole which will destroy anything which enters it. This is clearly not something that any theory now predicts. So this is a real problem. We cannot use now this solution, and this is why obviously I try other approach. I found out that someone else had this idea before, and this was a good thing for me to find out that Horowitz and Maldacena thought about posing a final state on the singularity of a black hole. Recently also Lloyd and Preskill wrote about it, and I think this is a very vivid area of research. The idea, which I'll now elaborate more on, is that post-selecting an entangled state of the infalling matter and infalling radiation would create a teleportation through which information could go out of the black hole. This is not so simple, but the idea is essentially this. We know since the days of Hawking that radiation is composed of two parties: the ingoing photon leaving the black hole, and the outgoing particle leaving the black hole, and the ingoing negative energy particle, which falls into the singularity. This kind of state is an entangled state, a maximally could be a maximally entangled state, which, when combined with this very spatial boundary condition on the singularity, can lead to teleportation. We have two maximally entangled systems, unless the evolution is non-unitary. We have two maximally entangled states, the radiation states and the radiation plus matter. And as I wrote here, using again, this is they described it, and in the consistent history approach, I now try to make it connected to the first part. So I described it using a two-time density matrix, and in this formulation we have the reduced density matrix, which again chooses for the outgoing radiation exactly the infalling state. So again, the final boundary condition on the singularity of the black hole encodes the information which will be later available. Later, not strictly later. But this is a very... there are many problems with this approach. One possible difficulty could be signaling from outgoing to infalling matter, but we know this could not happen. This would break causality, so this is not a real difficulty. More difficulty is performing some entangling interactions between the infalling matter and radiation, which will ruin the spatial boundary condition. The resolution of Lloyd and Preskill was to compromise unitarity, and I don't think this is what we want, because there is no approximately unitary process. Either it is unitary or not. So I prefer compromising the arbitrary final state. We need to choose a very specific final state. I don't think we know yet how to do it, but if we accept this assumption that there is a very, very unique final boundary state of the singularity, then this problem is solved. And another problem which could arise is the interaction between the outgoing and the ingoing radiation witnessed by an infalling agent. But now I use the first part, and what I think is the observer is a quantum object. It is macroscopically, it has many degrees of freedom, but eventually he would fall into the singularity, and we will be able to pose our final boundary state on it. So information is not lost. We can draw it from the observer. Of course, this is not the end of the story. Amps suggested their paradox 1 year ago, and recently Busso also criticized this approach. So, okay, this is in fact my resolution, and the resolution is the following. First of all, for an infalling observer, there is time of order m before, I'm not talking about very spatial black holes, but in the Schwarzschild metric, an observer has time of order m, but he is not able to measure within this time the Hilbert space of the matter, which is an exponent of m squared. So what he can do, he can have access only for a very, very small region in the Hilbert space. And this consists in a measurement Avshalom thought about, and we later wrote about it also. This is the partial measurement. This is what he can do, I think. The conjecture I want to make is, and I don't heard anybody making this conjecture, is also the observer outside the black hole can make only very specific measurements, namely weak measurements. And the reason I think this conjecture should be right is it is consistent with several approaches, such as the approach presented by Karlitz and Preskill, that radiation remains thermal until the very end of the black hole, until it reaches a Planck scale size and consists what we call a remnant. And the other approach, which I think is very related to this conjecture, is the modified information localization of Giddings, which tries to reformulate what we know about quantum information, but I think this is an essential part of proving this conjecture. Okay, the Amps paradox, I'm finishing in a couple of minutes. What they demand are three very, very basic requirements. First, of course, that the S matrix of the black hole is unitary, that information can go out. The other is that very near the outside region of the horizon, physics is described by the same classical field equations we know. And the third assumption, which is the most problematic in my opinion, is a freely falling observer experiences nothing out of the ordinary when crossing the horizon. Now, this is not really a problematic assumption. The negation of this assumption is problematic. So this is very shortly their argument. I won't go over it, but they showed without any doubt that there is a problem with the subadditivity of entropy. And finally, what I think is all their argument is based on the assumption that an observer makes measurements which let him know the number of photons that exist. The observer is capable of performing strong measurements. And I'm not really sure this is true, especially if we use the weak measurement assumption. Busso also criticized this approach, and again, one of these assumptions is performing strong measurements rather than weak. Other alternatives, which are, I think, less attractive, are Hawking's early idea of failure of unitarity, Hawking's current idea, which I don't think is fully ready, the apparent horizon. It can be that ingoing and outgoing particles are connected via wormholes, but I don't think this is the most simple resolution, as well as the resolution suggested by Avery, Chaudhry, and Pom of superstring theory with fuzzballs. The approach I tend to agree is the gradual reduction in entanglement, which I think can be a possibility, and of course the final state plus weak measurement approach, which I now suggest. This can obviously, this should be extended to other problems such as charged black holes, rotating black holes, with time-like singularity, giant black holes, and other cosmological singularities. Again, like Raphael suggested. So, free will. I think it is important because Yakir Aronov could not be here, but I think we all see that his legacy is here, and because it does not obey the arrow of time, his legacy would probably enrich us during the next decades. With him showing us so many paradoxes. And what he claims, and I cannot claim better, is to possess free will means we are free from the past, not from the future. That is, the initial state does not oblige us to do anything. As long as the future information is... Those are, of course, philosophical ideas, not physics, but as long as there is some part on the future boundary condition which is unknown to us, and if it is not too strict, what I want to say that if we don't know the future, we are not able to change it, and we will never be free of the future, but we will be free in the past, and I think this is the important freedom. And the other claim is that God is playing dice in order to save free will, and I, again, cannot say it better than him. The final, my final statement is, because we are macroscopic objects, we can enjoy both the robustness, the time reversal of the macroscopic world, and the freedom, which is part of the quantum realm. This is God's dice. Finally, the combination of final boundary condition and weak measurements was known for many years to be fruitful, but it was fruitful in the small-scale problems. Now I think that also in the cosmological scale, this is a very fruitful tool, and I tried to show that it can explain the apparent collapse we see, the boundary between classical and quantum regimes, the time reversal we want to believe is here, and also the bond rule we see. And it might also shed a new light on the information paradox, and very optimistically on quantum gravity. And this is not my opinion, this is again the opinion of Juan Maldacena, which is, in my opinion, one of the prominent quantum gravity researchers. So I want to say many thanks for you, Price and Matt, for letting me speak here, and also for my collaborators in the first part of the work, Yakir Aronov, Tomer Landsberger, and Eyal Ruz. I want to say a big thank you to Lev and Avshalom, which does not necessarily think like me, but really helped in this work, and also the funding of the Israel Science Foundation. Thank you.